y minus z into p upon yz plus z minus x into q upon zx equals x minus y upon xy. This equation is of the form pp plus qq equals r. To simplify the expression, we multiply equation throughout using x, y, z, so that the given partial differential equation reduces to equation x into y minus zp plus y into z minus x q equals z into x minus y once we multiply LHS and RHS using x, y, z. We can write the auxiliary equation for Lagrange's partial differential equation as dx by p equals dy by q equals dz by r. We have function p equals x into y minus z, function q equals y into z minus x, and function r equals z into x minus y. If we make use of multipliers, L equals 1 by x, m equals 1 by y, n equals 1 by z, and we evaluate the combination LP plus MQ plus NR, we observe that it gives us 0. Because when 1 by x is multiplied with function p, it becomes y minus z. When 1 by y is multiplied with function q, it becomes z minus x. And when 1 by z is multiplied with function r, it becomes x minus y. When we add up all these expressions, we get it as 0. When we multiply L, M and N to the numerators of these ratios, we have L dx plus M dy plus N dz. Similarly, the denominators are LP plus MQ plus NR. That is, we obtain L dx plus L dy plus L dz upon LP plus MQ plus NR. And since the denominator vanishes, when we equate each of these ratios to k, we can also have L dx plus M dy plus N dz upon LP plus MQ plus NR equals the same constant. Since LP plus MQ plus NR gets multiplied with the constant and becomes 0, we have L dx plus M dy plus N dz equals 0. Thus, we obtain this equation, and when we integrate both sides, we have integral dx by x equals log x, integral dy by y equals log y, integral dz by z equals log z, and we have constant of integration log c. We have log a plus log b plus log c equals log abc. Hence, this LHS becomes log xyz. Now, if x equals y, we have e raised to x equals e raised to y. Hence, since log xyz equals log c1, if we raise both LHS and RHS as the power of exponential function, we have e raised to log xyz equals e raised to log c1. Since logarithm is the inverse of exponential function, we have log xyz when raised as a power for exponential function, e raised to log xyz equals xyz, and e raised to log c1 equals c1. Thus, we obtain equation 1 of the form u equals c1. Now, we look for the second solution. When we choose multipliers L, M, N equals 1, and we evaluate the combination LP plus MQ plus NR, again we get it as 0. We have L dx plus N dy plus L dx plus N dy plus N dz upon LP plus MQ plus NR equals a constant k, and when the denominator LP plus MQ plus NR gets multiplied with the constant k, since LP plus MQ plus NR equals 0, we obtain L dx plus M dy plus N dz equals 0, where L, M, N are all equal to 1. When we integrate both sides of this equation, we have integral dx equals x, integral dy equals y, and integral dz equals z. We have the constant of integration b appearing in the RHS. This equation 2 is of the form v equals c dash. Looking at equation 1 and 2, we can write the general solution for Lagrange's partial differential equation as u equal function of b, or phi of uv equals 0, where u and v are obtained as the LHS of equations 1 and 2 respectively.